Okay, so all of what we're covering up until our next test is all about conic sections, and for most of us, this is a new topic. I'm not sure, does Algebra 3 cover conic sections at all? Does anybody remember? Couldn't say? Okay. Conic sections is looking at the cross sections of a double napped cone. So if you've ever been in a math classroom where they have this cone that you can take apart in pieces, it's because this cone shows you the cross sections of the cone. Now, it's not double napped. Of course, that would be hard to build a cone that would stand up. Okay. So you only see like the bottom cone right here. But if you'll remember from geometry, a cross section is defined as the two-dimensional shape that appears when you cut a three-dimensional shape. Like what shape appears at that cut. Okay. So the first one, which we don't really say a whole lot about, but you know about, we'll talk about it on Wednesday a little bit, is the circle. So imagine a cone. It has a circular base. If I take a two-dimensional plane and I cut parallel to the base, my cross-section is going to be a circle. Okay, that makes sense. Now, another shape that we're going to be studying this chapter is, what if I take that two-dimensional plane and I don't cut parallel to the base, but I go like in one side and out another side? It's still going to be a closed round figure. And some of us may call this oval. It's called an ellipse. Okay, so we'll do the ellipse and the circle on Wednesday. And the other two shapes are, what if you don't go in and out the two sides of the cone? What if you like go in a side and out the base? So the thing to remember about the double napped cone is it's not like this one where it stops. Like in theory, it just keeps going forever. So these shapes just continue forever because there really is no base to like finish it. Okay. And those two shapes are the parabola and the hyperbola. And we're going to start with the parabola. We're going to do the hyperbola on Thursday. Now kind of look at this image that I have on the board. What's the difference between the parabola and the hyperbola? Well, for the parabola, I'm going to come in one side of the cone. I'm going to come out the base of the cone, but I'm never going to cross the second cone. So my plane is running like parallel to the lateral side, so I only get one U shape. The hyperbola, you can see in the image there, is where I'm going to be crossing both cones. So if you could imagine the cone at the top, I'm going to cut that cone, then I'm going to come down and cut this cone. So the hyperbola has a shape, a U shape at the top and a U shape at the bottom. And they look like the same U, but there's two pieces, okay, as opposed to a parabola. So I'll pass around my two cones, and you can, if you want to touch and take apart, you can. Just be careful when you're passing, like I always hold it at the sides where the two pieces fall apart. Otherwise it might fall apart. And then here's my little one. This is my first and only 3D print. And by 3D print, I mean I sent it to someone and was like, print this for me. So those are the conic sections. Now, I will just make a quick mention about these conic sections down here. They're called degenerate conic sections. And they're like really like uninteresting. Like they don't actually form shapes. Like the circle, the ellipse, the parabola, the hyperbola. Be aware of these just in case you read anything in the directions in the textbook or anything strange happens. It potentially could be a degenerate conic section. Imagine if we cut the cones where the two vertices meet. That's a point, and that's not really anything to write home about, so that's pretty boring. If you cut through the middle of the cones from like the middle of the base to the middle of the other base, and you go through that vertex, you're not going to get a hyperbola where you have two nice smooth curves. It's just going to look like an X when you take it apart. Okay. Also, not really interesting. It's really just two intersecting lines. And the other one would be if you put a plane so that it lies on the lateral surface of the cone, if you remember your vocab from geometry, on the outside there. So it's intersecting at all the points on the side on a line. And then it goes up through the lateral side of the other cone. And so it just forms a single line. So we're not really going to study any of those degenerate conic sections. We're looking at the ones that actually form smooth curves. Okay, now let's get into the business of parabolas. We are skipping 10.1. 10.1 is about distance and midpoint formula, so I will not bore you with that business. Write this definition down. It has words in it that we don't yet know, but we're going to talk about them. And this is the definition that makes a parabola really useful in the real world. Oh my gosh. Just make sure you can put it back together. All of our definitions for the four shapes that we say will start off with a smooth curve graph. So remember, we are not looking at what we call the degenerate conic sections. They are not smooth curves. Okay, now I'm actually going to come back up to this definition, but we need to talk about the two words that we don't know, focus and directrix. So you've actually seen parabolas before, but you've looked at them through a different lens. When we studied parabolas back in first semester and in Algebra 2, we're looking at it through the lens of functions. Okay. Now we're going to look at it through a lens of conic sections. So we are interested in some different characteristics of the parabola. Some the same, some different. So we're going to talk about parts of a parabola down here, and I'm going to come back up to that definition. You could draw any shaped parabola that you want. I just snapped or took a picture from somewhere. Okay, put it on my slide. Okay, so it doesn't really matter what it looks like or where it is. We know some things about the parabola. Like, we would be able to describe a few things about this parabola. One thing that we spent a lot of time when we looked through the lens of functions was, what's this point that is the minimum or the maximum? And what do we call that point? The vertex. Sure. So vertex is a special point on the parabola. It's the min or max of the parabola. Okay. There was a line that went through the vertex. Does anybody remember what this line is called? Awesome. Axis of symmetry. It's the line on which the parabola reflects onto itself. And now that we've kind of reviewed those two, we can talk about what a focus is. A focus is a point that lies on the axis of symmetry inside the parabola. So the weird thing about the focus is it's not part of the parabola curve. It's inside the parabola. I always tell people when we first introduce focus, think about it like if you want to be the focus of attention, okay? If you have some kind of stupid human trick that you could do, double jointed, stand on your head, I don't know, something strange like that. If you were to come up here and do that, then we would all crowd around you and watch you do that. So you're the focus, you're in the center. Okay? So the focus is inside this parabola where the crowd is all around it. It's somewhere on the axis of symmetry. And depending on the shape of the parabola, the focus has like a guaranteed location. Now I'm just going to guesstimate where I think the focus might be. Okay, I don't actually know. So I'm just going to put the focus right here. It's on the axis of symmetry. It's inside the parabola. Where on that, I don't actually know. I'm just guessing. Thanks. The other thing that we need to know about to make sense of our definition is the directrix. So the directrix is not a point, it's a line. This line is perpendicular to the axis of symmetry. And it lies outside of the parabola. When you're graphing parabolas in this chapter 10, I'm going to want to see your focus, and I'm going to want to see your directrix. When you graph the directrix, it should never, ever cross your parabola. It's outside the parabola. It doesn't touch the parabola. So I'm going to put my directrix. It's a little bit crooked, I'm sorry. My directrix right there. Now, I always draw the directrix like a dotted line because then I know like anything that's dotted isn't actually part of the curve. It's like an asymptote or something that's there, but it isn't actually part of that parabola shape. Okay, now if I go back up to this direction, or definition, the parabola was a smooth curve graph, so that's the red part of my graph, in which every point on the red curve is simultaneously, so at the same time, equidistant to the focus as it is to the directrix. Okay, so what this means is I could pick any point on this red curve. I'm going to start with the vertex. I pick the vertex. How far away is it from the focus? 1 unit. How far away is it from my directrix? 1 unit, although my directrix is a little sloppy there. Okay, so they have equidistance. I'm going to mark them like with the congruent tick marks in geometry. If I pick any other point on this red curve, that also has to be true. So if I pick this point right here, if I were to get out a ruler and measure to the focus and measure to the directrix, these two lines would have to be the same for it to be a true parabola. Now, it probably doesn't look like they're exactly the same based on where I put my focus and directrix. That's because I'm just guesstimating where they are. But if I had the actual location of the focus and directrix, these two would be exactly the same. And that will be true all the way around the smooth curve. Okay. So that's what's special about a parabola. Okay. Let's look at equations. What are we actually going to be doing mathematically with this? Make sure you get these two equations in your notebook. Now, these are two new-looking equations for parabolas that you haven't seen before. There is some kind of connection to the old equations that we saw for parabolas. So my question to you is, does anybody remember one of the old equations for a parabola? A. Okay, that's one of them. Y equals ax squared plus bx plus c. Yes, and there's this one. It has an A in the front too. Okay, so those are the two versions of a parabola that we've graphed before. And remember, I said earlier, when we always looked at parabolas before, we were always looking at it from a function perspective. What does it mean if something's a function? Why is it good? Okay, Dylan says there's one output for every single input. So if I give you one of those equations, and I said everybody, and like let's say I use function notation, f of x equals, and I said, okay, everybody do f of 3. We all put 3 in, and you all get the same answer back out, right? There's only one output. Those parabolas could open which directions? Up or down. And because a parabola that opens up or down passes the vertical line test, which means it's still a function, right? So we were only concerned with parabolas that open up or down. Which one of those equations on my smartboard looks most like the old equations? X minus h squared, y minus k squared. The top one, because it has the x squared, right? So this top equation that I'm giving you in conic sections, this is a parabola that opens up or down. When I switch it and I don't have x squared, I have y squared. Now we're going to be seeing parabolas that open right or left. You've never graphed that before, because if you had a parabola that opened right or left, it didn't pass the vertical line test. It wasn't a function, so we weren't interested in it. Now we are. Okay, so that's something you'll have to pay attention to. Is my x squared or is my y squared? That will help me determine what direction my parabola opens. You may be thinking that the h and k's look familiar. They look like our standard form, y equals a times x minus h quantity squared plus k. Also the equation of a circle that you know from geometry. X minus h quantity squared plus y minus k quantity squared equals r squared. So h and k is going to represent the vertex of our parabola, just like it always represented for the parabola we studied in Chapter 2. One side note, k works differently now. That formula that Dylan gave me had a plus k in it, so k looked like what it was, right? H looked like the opposite. Now, in the equations I'm giving you, k has a negative in front of it, just like h does. So when you take them out of the equation, they both look like the opposites. Okay, so you have to remember that. When you take them out of the equation, they're always going to look like the opposites. P is called the directed distance from the vertex to the focus. So what I mean by that is if you have the x minus h squared, which is a parabola that opens up or a parabola that opens down, and your P is positive, then your parabola should open up. You're going to count up to your focus so that your parabola opens around it. If your P is negative, you're going to count down to your focus so that your parabola opens down around the focus. If you have a y minus k squared parabola, positive will be to the right and negative will be to the left. Directed distance, right? Negatives are down and left. I'm going to put a little quick note right here. The opposite of P is your directed distance to the directrix. So if you're counting up to get to the focus, then you got to count down to get to the directrix. One's inside the parabola, one's outside the parabola. And then this is really important to find your extra point. Your graph will not usually be a perfect parabola. Perfect parabola is one that fits the definition on that previous slide. but I at least want you to find 2 additional points that satisfy that definition. And the easiest way to do that, I'll show this to you when we do the example, is count 2p away from your focus. So write that down for right now, and then we'll talk about why that works every time.
Does that mean that 4p is equal to 8 in this equation?
Mm-hmm. Well, I think it will actually be, if you kind of move things around, it might be like 1 over 4p is a. Yeah. If you like solved for the y. But yes, 4p is, p is replacing the a, and so it's going to be responsible for like, does it open up or down, and or does it open left or right, and also like how wide it is. Okay, let's do an example. Jot this down in your notebook. We're going to do 2 examples. Get you ready for your homework. Now, you will be responsible for all the standard forms of conic sections. So think about that when you're doing your homework tonight. One thing that will probably be helpful for a lot of people is identify right off the bat, like, which equation does this look the most like? This one looks most like the top one, x minus h squared. Okay, so I'm going to write that down. We want it to look like x minus h squared equals 4p times y minus k. Does it look exactly like that? No. What are we going to do to make it the same thing? Easy fix. Get x minus k all by itself, or sorry, x minus h all by itself. Subtract to the other side. So we're going to move the 8 times y minus 5 to the other side. So this is x minus 3 quantity squared equals 0 minus is just going to be negative 8 times the quantity y minus 5. So first off, you got to make sure it looks exactly like the forms that I gave you. If there's like something, if there's something being multiplied in front of the x minus h squared, you have to divide that away. That's part of the p. It needs to be on the other side. You need to have x minus h squared all by itself. Nothing else over there. Okay, well, this is easy. What's my vertex, hk? What's that? 3, 5. Excellent. What's my p-value? 4p is equal to negative 8. Therefore, p is equal to negative 2. And that's a directed distance. It will either go down or left. Because this is an x minus h squared, I should be going down, up or down. So now it's negative, so it's going down. So I'm going to write off to the side here. Count down to the focus. And I could also say at the same time, that means I'm going to count up to the directrix. So do you think that might be helpful? Jot that down. Okay, well, I'm going to draw a graph. Here's my vertex, 3, 5. I like to label some of my points with V's and F's so I remember which ones are vertices and which ones are foci. I'm going to count down 2 to the focus, so that's just going down 2. So there's my focus point. You should be able to label the focus as an ordered pair. So if I was at 3, 5, and then I went down 2, I'm now at 3, 3. So I do know the exact location of the focus for this parabola. to get the directrix, I'm going to count the other direction from my vertex. So instead of going down 2 to the focus, I'm going to go up 2 to the directrix, and that's going to be a horizontal line. How would you write the equation of that horizontal line? Y equals. Horizontal is y equals, vertical is x equals, so this is going to be y equals, we went up 2, so we're at y equals 7. This is what I want you to practice on your homework tonight when you're doing the graphs. Whatever the book says, you can ignore the directions. Just pick the problems and for the graphing problems, just do these things, right? So find a vertex, find a p-value, graph, label your focus, label your directrix, because you'll be asked to do that on your quiz on Friday. Okay, now, by putting my focus in directrix, counting down to the focus, counting up to the directrix, I now know that my parabola opens down. Okay? And I know that it's going to open up around this focus like it's doing a superhuman trick, right? But I want to have a more exact graph than just draw it. So this is where getting the extra points comes into play. My directions for you for finding your 2 extra points that will satisfy the definition of a parabola are count 2p away from your focus. So put your pencil on your focus. What is 2 times p? -4. The parabola is going to be opening around this focus, so I want to count left 4. 1, 2, 3, 4. I got a point. Sorry, it didn't show up. Oh, put my thing there. Count left 4, so I got a point at -1, 3. And the parabola will show up on the other side, so I can count right 4. So I've got a point at 7, 3. And those are going to be 2 points that help get a better width of my parabola. I probably would have drawn my parabola a lot narrower than that if I haven't plotted those 2 points. And the reason why that works, okay, imagine a horizontal line through the focus. So I'm going to draw it with this red marker, this dotted line. Imagine a horizontal line through the focus. Any point on that horizontal line, when you compare it to the directrix line, is 4 away, right? Because when I was at the vertex, I counted 2 down and I counted 2 up. So whatever p is, it's double p away from the directrix. In order for your point to actually satisfy the definition of a parabola, it also needs to be that same distance from the focus. So then just count 2p away from the focus on that horizontal line, and I'm going to draw it in right here. 1, 2, 3, 4. There's a distance of 4 from the focus to my parabola, and 1, 2, 3, 4. There's a distance of 4 from that point to the directrix. So that's satisfying the characteristic of the definition of the parabola. And if p was 3, then they'd both be 6 away. If p was 1/2, they'd both be 1 away. So that will always work. Just count 2 times p away from your focus. Any questions for me? Okay, we want to do one more example. Make sure you put this one in your notebook. This is the one most people have the hardest time with in all the different shapes. As you're writing down the equation, what's different about this equation than the last equation? What's that, Maddie? It doesn't have those parentheses. So it's like, well, okay, sometimes you might not have the parentheses because like h is 0 and k is 0 and then it's x squared and y, right? But probably more concerning than that is that now there's no parentheses, but not only do I have a y squared, I also have a regular y. So I'm going to have to rewrite this so that they're in parentheses, which means I'm going to use my old tool from Algebra 2 and first semester. Dylan says, complete that square. Okay, so this one, because it has the y squared, we want to make it look like y minus k squared equals 4p times x minus h. Do you at least agree with that?
Sure.
Okay, so you want to complete the square for y's. You want to keep only the y terms on the left. Y squared minus 6y. We'll complete the square momentarily. And then you want to move everything that isn't y to the other side. So negative 4x minus 13. What number completes the square? 9. How are you guys getting that? Excellent. Half of the middle term and square it. When you square the middle term, it'll always be a plus. So you always put like plus 9 or whatever that term is. Half the middle term and square it if you need to write that down. And then by the laws of algebra, if I put plus 9 on the left, I've got to put plus 9 on the right. Okay, so remember to balance things out. You're good to go on the left side. The whole reason you did this is so that this would be a perfect square trinomial, which means it factors into the same two factors. Y minus 3 times y minus 3. So that could be rewritten as y minus 3 quantity squared. And on the other side, it looks like negative 4x minus 4. Now, you want it to look like the standard form that I gave you earlier, and on both sides you have the groups of parentheses. So one thing to make sure about like this x up here, the coefficient for that has to be 1. So if there's anything ever in front of x or y over on the other side, you have to factor it out, all of it. So there's a negative 4 in front of it, I have to factor out negative 4. So that'll give me y minus 3 quantity squared equals negative 4 times x plus 1. And now it looks like the standard form. So you're going to do a little bit of algebra manipulation there. Okay, now be really, really careful, you guys. What is my vertex? Negative 1, 3. If you said 3, negative 1, you gave me KH. You see how you're going to have to be careful? It has to be HK. Okay, p-value is negative 1. And this one was a y squared, so that means it's going to open left. So I would go left 1 up 3 to my vertex. I would go left 1 to my focus, which I'm now at negative 2, 3. I'll go right 1 to my directrix. So that's the y-axis, x equals 0. And I'll count 2p from the focus, which is 2 times negative 1, so that's negative 2, so I'm going to go down 2. That's at negative 2, 1, and up 2, so I'm at negative 2, 5. I've got this beautiful parabola. So something that you want to practice on your homework tonight is that, like, count 2p away, right? That's something that I know some people have a hard time with, so I want you to practice that. I am, for all of this week with my graphs, going to be posting my answer keys to homework online so that you can check your answers as you're doing it or after you do it and see if you've got the right points. The back of the book does it differently than we do it. They don't label everything. So if you want to make sure that you're getting the right focus and directrix and all that stuff, check online because I'll have my answer key up there. We've got just a few minutes left, and you do have a homework assignment. It's on your gold sheet. Like I said, I'll post answers online. I would say in general, if it's asking you to graph, ignore any other directions it may do and do what we did in our notes, right? Label vertex, label P, label focus, label directrix. Just a couple of quick things. You use parabolas every day. Satellite dishes are parabolic. The waves come in, reflect off the parabolic structure to the focus. That's where you get all your network, radio, whatever is happening there. Every morning when you're driving to school, you have your headlights on, parabolic. So you got the light bulb. Behind that is that shiny metal piece. Okay, that's parabolic. So when the light goes on, the light goes out to that parabolic shape behind it, and then it all goes out to the focus in a beam of light. Flashlights, headlights, awesome. Okay, and then projectiles, falling objects, we know those are quadratic, so they're also modeled by parabolas. A couple of quick things about your ACT, pre-ACT tomorrow. Be excited. Get some rest. Eat your breakfast. Dress in layers. You don't know if your room is going to be hot or cold. Bring your pencil. Bring your calculator so you're using the calculator you feel comfortable with. Bring a current school ID so you can check into your room. Be positive. It's exciting. An opportunity to show what you know. You guys are made for this. Just to kind of give you an idea, a 26 on the math part of the ACT is getting like between 40, 42 questions correct. So not everybody will complete all 60. You know who you are, who have trouble completing all 60 math questions in 60 minutes. I would say set your goal for 50. That way if you miss a few, you're still above the 26 mark. Okay, but you've like concentrated your time on 50 problems you feel really good about. That's a strategy for some of us who can't finish. But remember to answer every question. Pay attention to your room proctor. When they call to 5 minutes, look up at the clock. Make sure you've bubbled in those last answers. Choose all C's or all B's or whatever, but keep the letter the same. Mathematics. If you're not sure how to do a problem, try working backwards from the answers, plugging it in, working backwards, crossing off things that don't make any sense. Reminder on anything geometric, if you've got a visual there, unless they tell you otherwise, it is drawn to scale, meaning if something looks longer, it is longer. So if you solve and then that angle's smaller than something and it looks like it should be bigger, you want to resolve or rework that problem. Does that make sense? Okay. No area of a rectangle, base times height, area of a triangle, 1/2 base times height, area of a circle, pi r squared, SOHCAHTOA. You're ready. Have fun.
Can I borrow one of your ACT?